GLOBEBUSTERS!
And welcome everybody to GLOBEBUSTERs. We accept the reality of the world with which we're presented. It's as simple as that.
The GLOBEBUSTERS have started a new Thursday show called GLOBEBUSTERS Tech, where we strive to dive more into learning about our world through observation and experimentation. The raw, uncut show is about 2 hours long, and for convenience, I wanted to provide a summary, giving an overview of what we talked about. First off, we introduced our panel members. Cami Nodell, the wife of Bob Nodell. Her individual YouTube channel name is Aisling717. Next, we have Karen B. from the YouTube channel Karen B. Then we have Zack from the channel Good Times for All. And we have a new guy, Skylar, from the YouTube channel Troubling Tribune. And then we have myself, Kyle Adams, from the channel Kyle Adams. And now for the meat and potatoes of what we talked about. First off, we talked about refraction, and how this is a really important concept for flat earthers to understand, since some of the primary arguments against the flat earth are people saying, oh well, things appear to sink on the horizon, therefore that proves the earth is a globe.
The farther away a boat is, the more the bottom of the boat will disappear, and you'll basically just see the mast of the boat.
If you send a ship straight to the horizon, eventually it begins to disappear until it's no longer visible beyond your horizon.
Right.
And you should ask yourself, what kind of surface would produce that result?
That wouldn't happen if the Earth were flat. You would simply see the boat getting smaller and smaller and smaller as it went farther away, but you'd be able to see the whole thing with the same proportions.
The world is curved. I mean, it's a big curve, but it's curved.
These are supposedly the leading experts out there making this claim. But when we take refraction into account, it debunks their claim. The fish tank laser experiments are an excellent example of this. I've got a link to this series provided in this video's description. After that, we started talking about the refraction index and what that is. That got a little complicated, jargonated, and confusing. My understanding of the refraction index at the time was that the refraction index was a number given to indicate how much something refracts light. So I looked at where it said a vacuum has a refractive index of 1, and that made no sense to me. Why would nothing be able to refract light? Then it was said that the refractive index had to do with the speed of light, which, in the case of the increasing refractive index, made it appear like the light was going faster and faster when it entered into objects of greater and greater density. Which made no sense and was the exact opposite of everything I understood about refraction. Refraction is the bending of light, and an angle of 1 degree is still bending. In a vacuum, a beam of light shouldn't have any medium to bend it. So saying a vacuum has a refraction index of 1 was really hurting my brain. But since then, I've looked into this further, and I've finally been able to make sense of it. Simply put, the refractive index is a comparison to how much slower light travels in one medium as compared to a vacuum. Optical density is how thick or hard something appears to be. This means the greater the refractive index of an object, the slower that light is going to appear to move through that object. This is what causes that light to bend. But what about the 1? To figure that out, we have to take a look at the math. The concept for figuring out the refractive index of something is really simple. It's just a division problem. You just take the speed of light in a vacuum and divide it by the speed of light in your object. And here our object will be glass.
The speed of light in a vacuum is 3 × 10⁸ meter per second, and the speed of light in a glass is 2 × 10⁸ meter per second. After calculation, I get 1.5.
So the refractive index of glass is about 1.5, meaning light travels about 1.5 times slower through glass than it does a vacuum. It's all about comparing something to the speed of light in a vacuum. Even if you're comparing the speed of light in a vacuum to the speed of light in a vacuum. In which case, if you divide a number by itself, you get 1. The speed of light is traveling 1 time slower in a vacuum than it would travel in a vacuum. I think that's about as simple as it gets here.
Again, how it works in reality, not doing the math of it, but understanding how it works and that it's out there is really key to this.
The math for me is meaningless unless I understand it. So.
Well, yeah, and that's so true about every part of physics. Walter Lewin, my favorite physics professor, he taught at MIT for 4 decades. He said, if you only know the equations, then you know nothing. So you can memorize every equation. But if you don't actually comprehend what's taking place, you know, in the realm of physics between whatever you're looking at, then the equation really means nothing. It's just numbers to get that little piece of paper, you know, for taking a test. That's all that's for. And that's why how we got in the predicament we're in today.
Exactly. I was going to say that. It's like, that's the problem in the world today is, oh, well, here's some numbers and therefore you're wrong. I'm sorry, unless you understand what those numbers represent, and unless I understand what those numbers represent, just throwing numbers at me doesn't do anything.
Mm-hmm.
All right. Now, taking another look at the refractive index of glass, light is said to travel about 1.5 times slower through glass than it does in a vacuum. Exactly what causes light to speed back up the moment it leaves the glass is a whole other question. Cami explained that this is because light is not a particle.
Here they say light flat out travels in the form of waves. There are no particles. Like ripples in a pond, this forms the basis of crystal and gemstone optics. Notice we don't have any particles here. They don't work in gemstone optics. Gemstone optics rule out particles.
Polarized filters are another great way of ruling out the claim that light is a particle. I think this opens the door to so many different questions and just possibilities out there. One of the major questions that really crosses my mind is looking at the polarity of the sky. Why is the atmosphere polarized? If I just look at across the room and all of the air in the room, is that polarized? If that's not polarized, then why is the atmosphere in the sky polarized? Is it the atmosphere that's even being polarized? Maybe that's like the firmament that's kind of creating the polarization effect. And so there's so many different questions that I'm thinking about right now that I really would love to dive into. So this is a really good opener for the season.
Yeah, absolutely.
After that, Zack shared a glimpse of his mind-blowing second sun observation, which he discovered by observing the sky through a polarized lens.
This is the second sun video that we caught when Chris was over. Let's fast forward it a little bit. Let's see here. Yeah, I go through and I talk about what kind of camera it is and everything. Okay.
I think Cami already spoiled this one.
Yeah, this one blew my mind. Well, this shows you that there is something there's polarization going on in the sky.
But what's causing it?
Yeah, I don't know. But this is
Kyle thinks that would cause polarization. When you say what's causing it, things that I know would, there could be other things that are, but things that would cause polarization are like at our, what we call the North Pole, we measure an electric field and that going up. So crossing over through that column would polarize light. I think of that with a
an electric field can polarize light?
Absolutely.
Yes.
An electric field will polarize light.
Light is a magnetic field, an electromagnetic field.
That would be really interesting to observe with the Tesla coil.
Oh, mm-hmm.
Kind of put it in front of a Tesla coil, get that polarized lens, and just kind of look at and see what you can see.
You can. I mean, it would be the same as looking through a filter, so I don't know if it would be different if you cross it, and that is the Faraday effect, is simply the crossing of two filters of polarized light crossing over, and the light goes out. Again, what they talk about with all of this math and that are just simple optical effects, and if you look at the optical effects, if you understand the effects, you can pay somebody to do the math. I'm sorry. That's what I do. But yeah, no, understanding it is, or again on calculators, I have an Excel spreadsheet and everything. It does it well and doing it, but it's understanding what you're looking at. And if you start understanding what you're looking at, it's pretty darn fascinating. Polarization, as he brings it up, other places it could come into effect, and as we start working with it, eclipses.
I was just gonna say eclipses because that was the thing that I noticed when I went and watched the 2017 eclipse, that solar eclipse, because with the path of totality was close enough. I got to a good spot where I was like over 2.5 minutes. And it was just, I just started looking around and I was like, it's so weird because this light, everything gets darker, but it's not the same type of light getting darker as when the sun goes away. It's totally different.
It is.
And like weird things happen, like with the shadows on the trees and those weird like light waves that happen during totality. It's all kinds of crazy things go on. So there's definitely some crazy polarization effects going on during eclipses.
Our model also includes a firmament above our heads, which has refractive qualities allowing day and night to happen on the flat Earth, as well as the seasons. As to what it is made out of, we don't know, but if it's crystal, it could act as a polarized filter as well. So when we take a look at crystals and what they are capable of, it can give us a better understanding of just what the firmament is capable of.
What you have here is you have some fancy lines on here. And we're going to be looking through a piece of optical calcite, and something remarkable happens. This we're going to put into nonlinear physics. You're going to say that when I look through this, I don't get one line, but I get two lines.
And depending on what angle she's viewing it through, it changes. Is that not wild?
Yeah, that is pretty crazy.
Now go ahead and do some of the different optics that you can get. See how I can make it bend down. Look what I can do with the line with this crystal. No, we're talking about possible crystalline things in nature. Go ahead and look what I'm doing with the lines by moving this around just a little bit.
Now just think for a moment. If that red line were the path of the sun, moon, or a star, refraction could throw our view of it way off. And you can't use trigonometry to figure out how far away any of them are unless you know where they actually are. I hope you've enjoyed this summary. I think we can all look forward to a great season ahead of us. Thank you all for watching.
Who you gonna call? Yeah! GLOBEBUSTERS!
We will be back again next Thursday with a new show. Until then, be good to each other. Always be kind. Open your heart because there's truth inside. Peace out, everybody.
Peace.
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 We're gonna give Daddy the Rain Man suite. Do you dig that? We're going to Vegas, Mike. Vegas! You think we get there by midnight? Honey, we're gonna be up 500 by midnight. Ah, Vegas! Vegas, baby, Vegas!